frequency domain specifications. As like time domain specifications, in frequency analysis we have frequency domain specifications. So what are the uses of these specifications? Even the time domain and frequency domain, as a control engineer, we ask these specifications for the customer to design the controller or compensator. So these designs may be in time domain. For the particular application, you may have the rise time should be less than 0.5 seconds, or settling time should be less than 2 seconds, or peak hour should be less than 1.5%. So these are some of the specifications. Accordingly, we need to design the system. Similarly, in frequency also certain specifications where we need to take those specifications into consideration and we can design the controllers and compensators. Let us see what are the specifications available in frequency domain. So if you look at the list, so we have resonant peak and resonant frequency, bandwidth, cutoff rate, gain crossover frequency, phase crossover frequency, gain margin and phase margin. These are the specifications of frequency domain. Now let us see the one by one. Resonant peak. So resonant peak is nothing but it is the peak of the entire magnitude response of the system. So if you look at the frequency response, omega versus the magnitude. So when omega is varying from 0 to infinity, how the magnitude is varying, let us, a typical graph is like this. So in this entire magnitude frequency response, what will be the peak value? So the peak point is nothing but my resonant peak. So this resonant peak we are going to define for the closed loop frequency response. That means if at all you have closed loop transfer function, take the transfer function, find the magnitude, and for different values of magnitude, then you plot the different values of frequency, you plot the magnitude. That will be the closed loop frequency response plot. So in that, what will be the maximum peak? That peak is the resonant peak. So for any second order system, then we can derive a resonant peak, and this resonant peak can be written it as MR is equal to 1 over 2 zeta under root 1 minus zeta square. So zeta is a damping ratio of the second order system. Similarly, resonant frequency. It is the frequency at which the resonant peak occurs. We know the graph here. This is the resonant peak and the peak occurs at this frequency. This frequency is called resonant frequency, and we can easily derive for the second order system, and that is going to be omega r is equal to omega n into 1 under root 1 minus 2 zeta square. So these two, resonant peak and resonant frequency, are similar to maximum peak and as well as a peak time in time domain specifications. Next, bandwidth. What is a bandwidth? So bandwidth is defined as a set of frequency ranges at which the magnitude of g of j omega falls to 70.7% of its zero frequency, or the magnitude falls to 3 dB. So this is what the bandwidth of the system. So what is the bandwidth? It's basically a measure of the ability of reproduce the signal with noise rejection characteristics. So the bandwidth, we can derive this while taking a zero frequency value and also 70.7% frequency value magnitude. We can take down and we can derive very easily, and it comes to omega b is equal to omega n into under root of, so 1 plus 2 zeta square plus again under root, so we have 2 minus 4 zeta square plus 4 zeta power 4 radian per second. So this is the bandwidth of the system. So why the bandwidth is needed? What are the significance of the bandwidth? So using the bandwidth, then you can find out the rise time of the system, means how fast system is responding. So bandwidth and rise time are opposite each other. If you have more bandwidth, indicates the speed of the system is more than rise time is less. The speed depends on rise time, and rise time we can correlate with the bandwidth. Therefore, more bandwidth, more speed, less bandwidth, less speed. So this way we can use the bandwidth. Similarly, we can get the noise filtering characteristics using the bandwidth. and also, so this gives, bandwidth gives us the sensitivity to the parameter variations. In terms, we can say the robustness of the system we can find out using the bandwidth. Then what is the cutoff rate? So cutoff rate is a slope of the magnitude curve at cutoff frequency or nearby the bandwidth frequency of the system. Next, we have frequencies. One frequency is the gain crossover frequency. They are crossover frequencies. Gain crossover frequency. It is the frequency at which the magnitude of the system transfer function is unity. So it is a frequency at which magnitude of g of j omega is equal to 1, which is called gain crossover frequency. Similarly, we have phase crossover frequency. It is the frequency at which the phase angle of j of j omega is minus 180 degrees. So equate the phase angle to minus 180 degrees, solve for the omega frequency, which is the phase crossover frequency. So gain crossover frequency, phase crossover frequency, these two are of open loop frequency specifications, where resonant peak, we have resonant peak, resonant frequency, bandwidth and cutoff rate. All these four are closed loop frequency specifications. Now we have a gain margin. So it is defined as the reciprocal of magnitude of j of j omega at phase crossover frequency, which means gain margin, let us say gm, is equal to 1 over magnitude of g of j omega pc. So g of j omega is the sinusoidal transfer function, where we are substituting s is equal to j omega. Then we are getting the magnitude at frequency omega is equal to omega pc. So at omega pc, what will be the magnitude? That magnitude we can call it as, let us say it is mpc. Then gain margin is reciprocal of mpc. So gain margin is 1 by mpc, where mpc is the magnitude of g of j omega at phase crossover frequency. But generally this gain margin is expressed in dBs, decibels. So in decibels we can write it as gm dB. Gm is gain margin, dB in decibels is equal to, so 20 log of gain margin. So 20 log of gain margin. So we can also write it as, this log is base 10. So it is a logarithm base 10. Now 20 log 10, 1 over g of j omega at omega pc, or simply we can write it as 20 log 1 by mpc. So if mpc, if we take numerator side, then we can take it as a minus, therefore minus 20 log mpc. So gm dB, gain margin in dB, is equal to minus 20 log mpc, where mpc is the magnitude of open loop transfer function gh of j omega at phase crossover frequency. So we can also write the gain margin as, gain margin is equal to k maximum by k actual. So k is nothing but the gain, maximum is maximum allowable gain in the system. So if you look at any typical system for this particular system, so it is k by s into s plus 1 into s plus 2, and this is the root locus of the system. So this root locus is drawn on the s plane, and these two poles are in the left of the s plane for certain values of k, and they are moving from left of the s plane to right of the s plane. So when they are moving at exactly an imaginary axis, then we have two poles. And what is the corresponding k? So the k is 6 here. So this 6 is the maximum allowable gain in this particular system. So if you operate the amplifier gain k beyond the 6, system will be unstable, and within the 6, then system is stable. Exactly 6, system is marginally stable. You will have continuous oscillations. So therefore that value I want to take. And what is your actual gain? Your actual gain may be 3. The maximum allowable gain is 6. Then what is the gain margin? 6 by 3. The gain margin is 2, which means how far you are away from the imaginary axis. So imaginary axis is the borderline. From this borderline, how far away from you? So that is what the gain margin. If you have more gain margin means, then you are more stable. So the required gain to make you unstable is very large. That is what the gain margin is. So we can also define the gain margin as it is the amount of gain that can be added to the open loop transfer function or within the loop, so that my closed loop system will be at verge of instability. So if I this example, gain margin is 6 by 3 is 2. So 2 is a factor, that is the factor, the amount of the gain that can be added to the system will be at verge of. So 3 into 2 will be 6, system will be at verge of instability. So this is what the gain margin of the system, which is one of the very important relative stability and also time frequency domain specifications.